Hello students, welcome to our channel Creative Minds. In this lecture, we are going to discuss important concepts of quantum mechanics like Schrodinger Wave equation and also the concept of operators. In order to provide the sense and meaning to the probability approach, Schrodinger derived an equation which was known after his name as Schrodinger's wave equation. This equation is a keynote of the wave mechanics and is based on the idea that electron behaves as a standing wave around the nucleus. Now we will derive the Schrodinger wave equation. The equation for the standing wave is given as psi x equals to a sine 2 pi x over lambda. Here this symbol is pronounced as psi, and x which is showing the amplitude of the wave and is also known as wave function, and x is the displacement in the given direction, and a is a constant and lambda is the wavelength. By differentiating this equation two times with respect to x, we get d square psi x over dx square equals to minus 4 pi square over lambda square into psi x. The kinetic energy of the particle of the mass m moving with velocity v is given by the relation kinetic energy equals to 1 by 2 mv square. The total energy of the particle is the sum of kinetic energy and potential energy, and it is given as E equals to kinetic energy plus Vx. Here Vx is the potential energy. Rearranging this equation and by putting the value of kinetic energy in it, it becomes E minus Vx is equal to 1 by 2 mv square. Now multiply and divide this equation with m. We get E minus Vx equals to m square v square by 2m. According to de Broglie equation, lambda is equals to h by p, or lambda is equals to h by mv. Now taking square of this equation, it becomes lambda square equals to h square by p square, or lambda square equals to m square v square by 2m. We will replace this m square v square in this equation 4 by p square. So it becomes E minus Vx equals to p square by 2m. Now separating this term p square from this equation, the equation is rearranged as p square equals to 2m into E minus Vx. And now we will put this term p square equals to 2m E minus Vx in this equation, lambda square equals to h square by p square. This equation will become lambda square equals to h square by 2m into E minus Vx. Now we will substitute this lambda square equation from equation number 5 in equation number 3, which was d square psi x into d by dx square equals to minus 4 pi square over lambda square into psi x. By substituting this equation 5 in equation number 3, we get d square psi x over dx square is equal to minus 4 pi square over h square into 2m E minus Vx into psi x. Now we will replace this term h square by h by 2 pi, which is equal to h bar, and this equation becomes d square psi x over dx square equals to minus 2m into E minus Vx by h bar square. Now we will rearrange this equation in the final form, and we will get minus h bar square over 2m into d square psi x over dx square plus Vx into psi x equals to E psi of x, which is the final form of Schrodinger wave equation. Now we will discuss the significance of Schrodinger wave equation. It is used to describe the state of the quantum mechanical particles such as electrons present in atoms. The electronic structure of the atoms and the molecules can be well explained using Schrodinger wave equation. The wave function psi in Schrodinger wave equation gives the amplitude of the electron wave. The solution of the Schrodinger wave equation also gave the electronic band structure of the solid, and we all know that the solid materials, metals, semiconductors, and insulators can be classified using the description of the energy band theory. Most of the semiconductor properties, such as the origin of the band gap and the behavior of the dopants and the energy levels present in relation to the observed band structure, etc., can be well studied by solving the Schrodinger wave equation. Schrodinger wave equation is also called as Eigenvalue Equation when it is written in the form as h psi equals to E psi. We call the eigenvalue equation such type of equation where when operator operates on a function, we get some constant factor and the same function back. In this equation, the eigenvalue is energy and H is an operator which is called Hamiltonian operator. Quantum mechanical calculations are often simplified by using a property called orthogonality. To say that whether the functions are orthogonal, we mean that by taking the integral of the two wave functions corresponding to different eigenvalues of the same operator, we get the integration equals to 0. Eigenfunctions corresponding to the different eigenvalues of the same operator are orthogonal. Now we are going to cover the concept of operator. An operator is a rule that transforms a given function into another function. Following are the few examples of operators. Let d hat be the operator that differentiates a function with respect to x, as shown in this equation. Similarly, 3 hat is the operator that multiplies a function by 3. And the sum and the difference of two operators a hat and b hat are written separately as shown in these two equations. If an operator has more than one variable, then it has the following effect. Let us take this example where this is an operator and these are the two variables. We will write this operator with these two variables separately, as you can see this in this example. The product of two operators a and b is defined by this equation, and you can see this from this equation that we first operate the operator which is on the right hand side of the operator product, and then this resulting product is then operated with the operator on the left hand side of the operator product. The operators a and b, ab and ba may not have the same effect. Consider, for example, the operators differential operator d by dx and x, which is simply the multiplication by x. So when these two operators are operated, then by changing the orders of them, we see that their results are not the same. So we can say that the AB and BA are two different operators in this case. Operators obey the associated law of multiplication, which is given as A into B into C equals to AB into C. And you can see this clearly in this example that this law is obeyed by operators. The only difference between the operators algebra and ordinary algebra is that the numbers obey the commutative law of multiplication, but operators do not. And in quantum mechanics, a commutator of the two operators is given as a commutator of a and b equals to ab minus ba. If ab is equal to ba, then the commutator of a and b is equal to 0, and we say that a and b commute. If ab is not equal to ba, then a and b do not commute. Now we will look into the role of the operators in quantum mechanics. Schrodinger Wave equation, which is known as Eigenvalue Equation, use the operator called Hamiltonian Operator, which is given as minus h bar square over 2m into d square by dx square plus bx. The linear it is an energy operator. The linear momentum pq is replaced by an operator given as minus iota h bar del over delta q. The operator corresponding to p square x is given as minus h bar square del square over delta x square. There are many other operators which are used in quantum mechanics. We will cover another concept of quantum mechanics called particle in one-dimensional box in our next lecture.